Hello, my name is Yingshi Zheng, a senior mechanical engineering student in University of Michigan. This summer, I participated in the Summer Undergraduate Research in Engineering, or SHO program. I work with Professor Don Tilbury from Mechanical Engineering Department, and my project is Obstacle Avoidance for Teleoperated Differential Drive Robot, or OADDR. Now I will introduce my project in detail.
Teleoperated robots are widely used in places and situations when they are inaccessible or hazardous to humans, like post-disaster areas. Human operator receives feedback information about surroundings through cameras or sensors in real time, and remotely control the robot. However, unavoidably there exist obstacles in the real environment, and human operator may not be able to avoid them due to limitation of vision. The project's main goal is to have an obstacle avoidance controller built in the teleoperated robots and take charge of the robot's movement when human controller lacks the capabilities of avoiding the obstacles. The robot I used for the project is called the SuperDroid. This differential drive robot moves based on separately driven wheels on either side of the robot. When robot turns left, the wheels on the right side will turn forward, while those on the left will turn reverse.
Apart from the basic robot control and moving system, the camera is used for detecting the obstacles' positions. In the project, I use April tag, simply a 2D barcode to represent the obstacles. On this test program, the tag is highlighted when it's detected and is shown on the right screen for its actual positions to the camera.
The router allows users to control the robot by gamepad wirelessly and allow data communication among different subsystems. The method I'm using to implement obstacle avoidance is called the steering potential field method. It regards the obstacle as repulsive potential field to the robot. Robot will move where there's least potential. It controls the robot's turn rate and also the velocity of the robot when moving closer to the obstacle. It uses angular width and the distance to the obstacle, so that a larger and farther obstacle will be of equal impact on the controller's behavior as a smaller and closer one. Camera will detect obstacle's position dynamically, but when the obstacle is out of sight, I assume it's still at its latest position. The arena with April tags on the floor and the wall helps with the localization. Because each distinct tag has its unique position predefined in the program, camera will detect those floor and wall tags and get the position of the robot. Then tag's local position is recovered by its arena position recorded before. Thus, OADDR program can handle the situation when cameras can't see the obstacles. Now let's talk about the working principle. This graph shows how each subsystem works and how data is transmitting through subsystems by lightweight communication and marshalling, or LCM. In short, the whole program has a parallel structure of gamepad and automatic controller. The branch of gamepad controller will read the data from the gamepad and output turn rate and speed, which are applicable to drive the robot. The branch of automatic controller will calculate the according turn rate to avoid the obstacles safely and reduce the speed to allow in more responding time to avoid the obstacles. Afterwards, the chassis driver code will receive both sets of turn rate and speed. Automatic controller will work when gamepad's turn rate is not enough to avoid the obstacles. Finally, robot will move based on the appropriate command and return encoder's values as a feedback. In the future, the gamepad and the automatic commands will be blended together in chassis driver code to allow them working and save time. Apart from basic obstacle avoidance function, the wall avoidance function will prevent the robot crashing into arena's walls. They both work in either forward and backward movement. Rumble feedback will be provided to gamepad to warn user that his previous command fails to avoid the obstacles, and all the functions could be shut off and turned on through the buttons on the gamepad. Now it comes to the exciting showtime. Let's see how OADDR can perform in the real world. The robot is moving towards the obstacles. The automatic controller helps me avoid the obstacles. I can hear the very strong rumble feedback from the gamepad. Here comes the backward movement. Yes, it can do in both directions. At this time, the speed is reduced. This is to prevent the robot from moving too quick to the obstacles so that there's no time to respond. When there's two very close obstacles, the automatic controller will also manage the robot to moving in between. I really enjoy doing this short project. Finally, I would thank Justin, Steve, John, and also John from Professor Tilbury's group for their help.